So welcome to the third technical exchange meeting organized by the CCTF working groups on TAI and algorithms. Today, you will hear a series of talks on the fundamentals of getting started as a UTC contributor. And I'm Elizabeth Donnelly from the NIST Time and Frequency Division. I serve as the chair of the CCTF working group on algorithms. The topic of today's exchange is the fundamentals of getting started as a UTC contributor. We will have another technical exchange 2 weeks from today. And we're having them back to back so that everyone's fresh for the second one. And the second one, the topic will be case studies from UTC laboratories, up and coming UTCK labs, and UTCK labs implementing expanded capacity. And hopefully many of you can make it for that one as well. It will be at the same time. And Patrizia will put a link into the chat so that you have it handy for registering for that one as well. So without delay, we can get started with our program. So our first speaker is Dr. Jeff Sherman. Jeff has a PhD in atomic spectroscopy, studying trapped ions from the University of Washington. He's been with the NIST Time and Frequency Division for 14 years and has worked on a broad variety of clock projects and timekeeping projects. And he currently leads the time realization and distribution group at NIST. And he's responsible for many things. He's also managing the day-to-day operations of the timescale, two-way satellite time and frequency transfer, and a lot of other projects. And Jeff will tell us about the hardware and software requirements for a UTCK timescale lab. So welcome, Jeff. And I'm looking forward to your talk.
Thank you. In this mode, I can't really see anything. So let me just ask, is my audio working? Is the video unobstructed?
Yes, and it looks good, thanks. And I'll let you know if when people have questions.
Okay, thank you. Thank you, Liz. Good morning, good evening, good afternoon for some. You've already been introduced to our division chief, Elizabeth Donnelly. At NIST, the activities of the timescale, the primary and secondary frequency standards, 2 radio stations, and a very large network time program are organized under this group, the Time Realization and Distribution Group. Here are the folks in Boulder, including a few visitors from other laboratories who were able to stay at NIST for a few months. The intended audience for this talk is really non-specialists or new or smaller labs, those considering building a UTC-K realization. The pace will be a little fast, but don't take notes. The slides will be available. I think the recording is in progress, so you'll be able to rewatch. There are a few unintended messages. I don't intend to endorse any particular company or product or method. I don't recommend you merely duplicate NIST's choices and methods for no other reason. And I'll cover the basics only: no experimental or advanced clocks or frequency standards or time transfer techniques or anything that's not available commercially. And finally, there will be advice, but it will be only delivered by bears falling from trees, just like this guy. Why should you do such a thing as participate as a UTC-K laboratory? Well, it's really only available and recommended for legal and practical authorities within a country. UTC is an approximate source of the SI interval second after figuring for relativity, and the SI second underpins all of dimensional metrology these days. BIPM's publication, Circular T, is the only thing that establishes mutually recognized records, establishing traceability between your UTC-K realization and UTC, between the realizations and each other and primary rate standards. And you may find national industries and agencies within your country are starting to demand this. Finally, participants contribute observational data, which helps build or realize UTC itself in the way we'll talk about later this talk. How do you become a UTC-K contributing laboratory? Well, step one really is read carefully all the references listed below, and then read them again 2 or 3 more times. After doing so, you'll find the first step is to describe your intentions and the layout of your laboratory and equipment to the consultative committee. Build and operate a local laboratory time standard we will call UTC-K with the goal of realizing an offset below 100 nanoseconds. Measure and report this time standard to BIPM via an approved link method that will likely involve GPS or GNSS viewed in common view. Measure and report 1 or more free-running atomic clocks with respect to your local standard and submit that as data to the BIPM. And there is no step 5. This is pretty much the minimum. After having done this, though, you'll find you have a very useful resource, UTC-K, which can be distributed as signals or calibration services within your country. You can embark on developing a primary or secondary frequency reference, experiment with an atomic ensemble, do research and development, etc. But none of this is really essential activity related to the UTC-K realization. This talk will only focus on these 2 activities because the next talk will talk about the link method. The whole business is that we really take seriously the idea that we are going to tell what time it is by counting religiously the periodic emissions from a standard that we believe is stable in rate. In other words, as periodic voltage waveforms come out of this device, we're just going to count them and assign a nominal time period or interval to each period of oscillation and sum them up. So if you walk into any lab, you'll see a forest of cables connecting measuring devices to these electromechanical oscillators or clocks. And so this forms the first building block you got to get right, is you're going to be distributing these signals through cables. If possible, it's important to get cables that are double shielded, and if the cables are long, to avoid Teflon dielectric materials. So-called expanded polyethylene materials are lower loss and have a much better temperature characteristic. In general, the rule is that the larger the diameter of the cable, the lower the loss. On the other hand, for very high frequencies, they cannot propagate single mode in large cables, and you have to accept the smaller diameter. But this is a concern up in the several gigahertz regime. And once you're familiar with the menu of cables, you'll also have to be familiar with the zoo of connector types. The ones listed in the top 4 here are the most common, but you at least need to be aware of some of the less common ones. They will show up in equipment. And of course, you'll need a basket of adapters to work with all of these. Here's the falling bear with the first bit of advice, that a cheap cable can easily become the most expensive thing in the lab, because in our experience, they tend not to fail completely. They fail in sort of a half working state, making it very difficult to diagnose problems, and they can sort of sit causing chaos for months and months and months before you identify just what's going wrong. So it's important to get these cables built nicely. It's important to know that the cables are really unbalanced radio frequency transmission lines. You need to know about termination of load impedances, matching source impedances. In general, you're not allowed to use these so-called T devices, although there are exceptions to this rule. And it's really not because of damaging equipment concerns. Really, it's about controlling reflections within cables and interfering signals, which very tiny reflections and interferences can cause large phase shifts at a measurement. So if you're not allowed to use Ts, you're going to have to learn about a device called an RF distribution amplifier or isolation amplifier, which allows you to duplicate signals with low additive phase and amplitude noise, but especially high input to output isolation and output to output isolation. They're purpose-built to have low noise at very high signal levels of maybe 10 dBm or higher. I show on the right a plot of their several commercial distribution amplifiers' noise characteristics as the Allen deviation times an averaging interval tau, which is a good measure for time predictability as a function of time. And it shows in relation to two commercial atomic clock types according to their specification. So largely, you don't have to be concerned with which one you buy if you're operating standards like cesium beam quality, but if you're operating hydrogen masers, you can see there are some choices better than others. The notion of taking this idea seriously means that we want a high reliability device that counts periodic oscillations from the clocks. And if you count by the nominal frequency of the clock, the counter itself now outputs a register of interval seconds. And the idea is that we sort of imagine treating one rising edge, for example, of pulses out of this machine with a particular second in the UTC timescale, and then never lose count. And in practice, these devices have an extra feature, which is that if you bring a reference timescale or a redundant timescale realized in this way as pulses every second, then there is a way to trigger a manual synchronization that can reset the counter to zero, effectively tying on to the next zero crossing of the oscillator and providing alignment with your timescale and the reference timescale to plus or minus one period. Now you've made a different kind of signal, this sort of pulse waveform, so you need a different way to distribute it. And here I want to highlight an open source, open hardware version that was developed by Anders Wallen at the Finnish Institute. Here's a schematic showing the output stage, how it couples strong currents to drive long 50-ohm cables, and a very nice feature that allows you to carefully tune each output channel's delay with a variable capacitor, meaning you can align the outputs to a very fine level. I built one of these and also tested its temperature dependence. It's quite good, especially the output to output temperature dependence is essentially negligible. Once you've made these pulse references, you need to know how to measure differences between them. And a fundamental instrument is known as the time interval counter or time interval analyzer or variations on that name. It's a 3-port device where you're going to give it two pulses on inputs called start and stop, and you're going to give it a reference so-called time-based signal, which is radio frequency. And although the devices really work in a different way, you can consider the device as just counting the number of time-based oscillations between the pulses with the ability to interpolate phase between periods of the time base. There's some general rules that, for example, if you give it a time base that is accurate to a part in 10 to the 11, it means that you'll accumulate no more than about 10 picoseconds error for 1 second intervals between start and stop. And you have to choose some configuration standards, like the exact trigger voltage you will consider to be the measuring point for each pulse. The device has different internal termination options, filtering options, and the devices often change their effective calibration for start-stop reorderings. In other words, time intervals that go through zero. So you need to decide on a standard of how you're going to keep the time interval strictly positive or strictly negative. Here's some example of how well you can do with these devices. In blue is a commercial device tested with matched cables, and in orange is an open hardware device you could purchase at very low cost from a nonprofit. And you know you're doing really well when what you see is the quantization noise in the time interval counter itself. The time deviation plot on the right shows that with just about a minute of averaging, either of these solutions are making measurements with significance down in the few digits of picoseconds. Ticks also illustrate a useful principle. So suppose there's some system that you want to measure the delay through, either a cable or something more complicated. What you do is you build a system measuring with a time interval counter that doesn't involve cable or system D at all. And cables A and B in this example don't even have to be matched. You then insert the system under test and effectively compute a differential where a lot of the systematic biases simply drop out. And the bias that you add in the form of this adapter to shoehorn in cable D is negligible. There are a lot of lessons to take away from this. It's that differential techniques are great because they demand stability and linearity, but not absolute accuracy of everything in the experiment. And stability is typically easier than accuracy. We've just learned the statistical variation of these measurements can be put below 10 picoseconds after just a few seconds of averaging. And it turns out that 10 picoseconds is almost always good enough. For example, BIPM clock reporting data is quantized at 100 picoseconds. You'll learn that the stability of various link methods are at about the level of 50 picoseconds or worse. And 10 picoseconds of noise averaged over 1 day is only a part in 10 to the 16 in frequency, which is better than primary cesium frequency standards averaged over 1 day. Right. We're also going to need to know a bit about atomic clocks. We won't go into it in this talk. There's an excellent review article that talks about all sorts of commercial technologies, but we really want to focus on the clocks that can give you about 100 nanoseconds of error over a month and qualify as a reportable clock to BIPM. And really, there are just a few technologies that can accomplish this. Unfortunately, no warm rubidium vapor clock, even the best one, really approaches this level. Instead, we're left with the cesium beam technologies, hydrogen maser technologies, and recently come to market are laser-cooled rubidium clocks, shown here in black. Every clock eventually needs correcting. That plot I showed before illustrates the principle that even ideal clocks are sources of white Gaussian frequency noise, but that means that the phase of the clock random walks as time evolves, and it means that every clock needs correcting. So you need to be familiar with how to adjust the clocks. The simplest method we could call the direct steering approach, which is that there may be some analog controls, like literally a screw that you might turn on the device for very coarse frequency tuning, or some digital control of a synthesizer inside the device where you can tune the frequency or even accomplish very fine tuning of phase by timing two temporary frequency adjustments. The only downside of this approach is that it obscures the free running clock behavior unless you diligently log every time you steer it and exactly how you steer it. And some of the clocks come with a sort of annoyingly coarse tuning. The other approach is to tune a synthesized offset from the clock. There are very special synthesizers meant for synthesizing very small offsets from the nominal input frequency. These have additional cost and another device that can fail. On the other hand, it leaves the free running clock alone to be directly reportable to BIPM. And it separates concerns so that replacing the source of a UTC-K is easier in the sense that now these two components are modules. A survey of the community shows that about 2/3 prefer an offset generator of one type or another, and about 1/3 directly steer a component within the clock itself. And about half the community uses a cesium beam clock directly to realize UTC-K, whereas half the community use a hydrogen maser. So there are two ways to steer the clock, either directly or via an offset generator, but in either scenario, the principle is the same. You should use all available resources to estimate the steered clock's offset, but really you should try to minimize your dependence on GNSS, ideally to 0. And you'll find a choice between achieving good stability of your UTC-K rate and the desire to keep the absolute offset small. Because of the delay inherent in getting information and the noise types that we observe, it's really not possible to optimally do both of these goals. You need to strike a balance. We now have all the components to write down on a single page a minimum UTC-K realization. This is really it. A single steered clock. It's frequency distributed, so we can attach many devices. The pulse counting, cycle counting mechanism that creates a UTC-K pulse and its distribution. And at one point of the distribution, we will count as a reference. And this is really it. The next talk in the session will describe the only remaining major component, which is a specialized GNSS timing receiver or other link method meant so that BIPM can observe your UTCK. Here I highlight in yellow a particular radio frequency path to the timing receiver as special. For the most part, it's important to define the UTCK reference point in the pulse. That seems to satisfy most means, but you'll find that the timing receivers use the radio frequency phase for increased resolution. So it's important, especially to keep that path constant once calibrated, and attach this additional time interval counter I show on the bottom to measure the delay through the timing receiver. And I'm sure the link talk will expound upon this, but I point it out because it's an exception to the rule of the pulse really being the best place to consider as a reference. Some of you may be thinking, wait, is this enough? There's only one atomic clock, one steered clock, and that's all they have in this minimum realization. But it's true. The BIPM itself in the guideline document for clock reporting explicitly gives the case of what your report looks like when you only have one clock. Its time is identically 0, and it's reported just this way, and there are no other clocks at the hypothetical laboratory. This is a good schematic to start with because you can easily add free running clocks as your lab grows. You just buy one additional time interval counter and one additional pulse distribution means for each atomic clock, both of which are negligible costs compared to the atomic clock itself. And the output of these additional time interval counters now pile data into the so-called clock data that gets submitted to BIPM. So the advice is to build your lab gradually. The most important thing is to get on circular T, and so focus on the minimum first. You then have a traceable and calibrated UTCK source from which you can build services within your country, and after which now you have time to add additional clocks and resiliency features or experiment with higher precision techniques. So to review, the big picture, what are you trying to do? For the steered output UTCK, you're trying to establish a record and forecast of its offset with respect to UTC or other interesting standards like GNSS or other UTCK realizations. You're trying to apply gentle frequency steering to keep its offset small and stable with respect to UTC. And you're allowing the BIPM to observe UTCK continuously via an approved link method. For the free running clocks, you're trying to establish a record and forecast of their offsets with respect to your local standard and other free running clocks. You really are just trying to keep the clock stable and monitor any telemetry that the clock can report about its health. And if you submit the data, you allow BIPM to use the free running clock to build its free running atomic scale EAL and the derived products TAI and UTC. You may be thinking, what about clock ensemble algorithms? Well, I emphasize they're not required. They add a lot of complexity, and really they give benefits only when your lab has many, many clocks. So I urge you to focus instead on the first few clocks being treated as online backup sources rather than parts of a complicated ensemble. There's some specific machinery for reporting clock data, and here on the right, I show some lines from NIST's file for April. The idea is that you just report a measurement of the UTCK time versus every clock every 5 days on modified Julian dates ending in 4 or 9 to nanoseconds units to tenths of nanoseconds precision, shown here in yellow. Your lab ID and a file name prefix will be assigned by BIPM, shown here in blue. The clock identifiers are a combination of the clock type or manufacturer in red and a unique identifier to your lab. BIPM has offered a website which can generate these serial numbers for you. If the clock experiences a step due to, for example, changing its cable length or repairing a broken device, it's important to report the nature of the step, and there's a sort of metadata format in which to do that. I encourage you to read the document. You transmit the data as early as possible, but definitely early in calendar month X+1 for nominal calendar month X. And currently we do so through the file transfer protocol to a specific directory you will be assigned by BIPM. The participation in UTC Rapid is the same. You do the same sort of thing, but you measure the time every single day, and you need to transmit the daily file within 2 days of measurement. This is just a summary of the relative growth of the number of clocks currently reporting this way. There are about 408 now in total, and they're about half masers and cesium by number. How do you initialize this whole business with the name of the second? Well, the simplest and most practical way is probably to use some sort of network time to other UTC-K realizations. The network time protocol is likely going to be available to you. You'll probably be running network time protocol appliances anyway. I did some spot checks from the US to far places like Japan and Australia, and the network delay, the worst case bias is less than 100 milliseconds to both places, likely sufficient anywhere in the world. You could probably even use the so-called web clocks, especially those that measure the network delay and display it as part of its calculation, although you should beware added latency in operating system and display. Similarly, you can use radio signal emissions, either radio-controlled clocks, or you just tune in and listen to the broadcast. There are web-enabled listening devices, but these add hundreds of milliseconds of delay. So if you're trying to get the second right, you need to be extraordinarily cautious if you do this. GNSS receivers can also be used, very likely anything out of the box with any antenna cable and any delay likely to be within your lab is sufficiently good for getting the name of the second. But you do need to know about the latency of the device's serial data message. And especially manufacturers often have different conventions between the message labeling the pulse that just happened or the pulse that's about to happen. And so this is a way to get the second wrong sort of on accident. Finally, so far, I claim that you could do all this with the time interval counter, but the reason people measure RF phase instead is for higher precision. For a new lab, I would dissuade you from doing this because these devices are more difficult when there are faults or restarts, or the device has to be rebooted, or a cable has to be changed, because one way or another, you have to figure out the lost number of RF cycles that happened during the disruption. On the other hand, I wanted to recommend tiptoeing your way into this as a new lab. And so I show here below a sort of way to get into this slowly through thinking of sampling the RF waveform like a digital oscilloscope might. You can use devices known as software-defined radios, commercially available and at quite high performance if pushed. And then there are multi-channel and very novel devices that are really at the state of the art of time resolution using radio frequency phase. I want to show you just one example. This is a multi-channel device we use here at NIST. And what I'm showing is the same clock input into all 16 channels. The time series at left just shows the differences. All of these should be flat, noisy lines. And at right, I show the time deviation of the same data. It really asks more questions than it answers. Anytime you look at measuring zero, you're going to find something you didn't expect. And here you can see some kind of coupling to temperature in the lab or other RF interferences. And groups of 4 channels seem to do similar things. They take steps in phase, all of which are at this few digit of picoseconds. But I really pointed out to show that there really is no perfect. The closer you look, the less perfect you'll find. And good enough is the order of the day. It's important to guard your system against power fluctuations, failures of cooling, lots of disasters that can happen in the lab. Many clock devices will accept DC auxiliary power sources. If they don't, you can build auxiliary power your own using this so-called diode OR circuit shown on the right. Many clocks will charge and use an attached battery bank, and you can often expand the batteries a bit. And there are commercial devices known as DC UPSs, which charge and manage a battery bank you can make use of. There are useful devices called rack-scale automatic transfer switches that derive power from 2 AC sources with relays that switch between whichever is active within a few milliseconds. And of course, uninterruptible AC power supplies, which span a variety of techniques and expenses and disadvantages. I will say that our experience is the so-called standby devices are the least expensive and the most likely to fail exactly when they're needed, likely because the DC inverter springs to life only when the AC utility power goes off. And that's probably a sort of violent event for electronics. Our most dependable devices have been the so-called online or double conversion devices, which run the inverter all the time, meaning that if they are going to fail, they're likely going to fail during a normal period when the utility power is on, and you'll be able to handle it without losing the things that are powered by the device. Your lab should write a list of priorities for how you're going to power the devices. And every lab might order these a little bit differently, but for sure, the atomic clocks and the steered outputs and the derived pulses and distribution are the most important, and thankfully, the lowest power and easiest to supply direct battery backup. On the other side of the scale, it's very hard to power cooling because of the high power consumption requirements. And you may need diesel or natural gas generators to really try to have backup power for any cooling method. It's important to build with redundancy. Atomic clocks have a lifetime between 8 and 15 years, and they do tend to fail early on occasion. You need to be prepared for it. Having redundant measurements and redundant clocks will be the first clue of malfunctioning, giving you early warning to fix things before it's critical. Of course, you don't want to get carried away. Redundancy scales linearly in cost and complexity, but you gain no benefit until there's a disaster, which is rare. So a good approach, a balanced approach we follow is to have a primary and an alternate system, which are two nominally identical sets of devices for operating at the best or the best desired performance level. Have a plan for operating at reduced performance if the primary and alternate fail, and then have some sort of a plan if you experience a full facility failure. Another important redundancy is personnel. It's very important to document and share regular status updates about the state of the timescale. Promote a sort of shared cause with your colleagues. Informed colleagues are a very efficient mutual aid defense strategy. If they know what's going on in your project, you know what's going on in theirs, you can back up each other very efficiently. Everything I've said goes double for outdoor equipment. In this case, an antenna was damaged by flying construction debris in Boulder, Colorado. So plan extra cabling and mounting points and antenna spares for anything that goes outdoors or on roofs. Finally, some bad news. There is no single degree or training program that is appropriate for this industry. There's no single company or product that can meet every one of our needs indefinitely, and whatever you build is eventually going to break or need to be changed. You and your staff will need to learn a little bit about hardware and construction, repair of equipment, laboratory hazards and their mitigation, electronics, redundant power systems, software engineering, at least a little bit, computer networking, and a little bit about heating and cooling and air handling. The good news is that this community exists to help, exchange advice, provide visiting training opportunities. I encourage development within the regional metrological organizations or reach out to me. A little note for software engineering, I've found Python to be incredibly useful. I won't read through this list, but the table is meant to be a source for you to argue with your colleagues about whatever their favorite tool is. There is a way to do it for free and no licensing with Python today that's portable between many operating systems. So copy the table below and have your arguments. A very typical software pattern in the lab is that you'll want to isolate the continuously operating portions away from the general laboratory network, connected with private networks or serial buses only, and everything in the box you want to attempt to keep up 24 hours a day, 7 days a week. The software that you write inside the box should be kept as simple as possible and focus on data collection only. The later analysis can be done after moving the data out to a general purpose network, where the final step is to format it in the means that BIPM requires and send it via the file transfer protocol. At this layer, you might also do some automated alerting, since this layer has connectivity to the rest of the internet, including an old-fashioned modem to physically dial phones in a way that doesn't depend on the internet. You can also send text messages or chat-like apps to give critical conditions within the lab. We found it useful to automate sort of typical plots of ongoing experiments and equipment that we run. And this system should be designed to test itself daily. And the lack of a test result should be a clue that something has happened to it, and your clue to go in and see what's gone wrong with the alerting itself. Finally, it's important to verify that you submitted correct data to BIPM. And so you can automate so-called integrity checks by re-downloading your own data and applying sort of a different, more basic analysis scheme to make sure that it is valid and the data makes sense. Finally, with respect to hardware and software implementations, I think this rings true, and it's a source of frustration for all of us that nothing is more permanent than a temporary solution that works. You'll find that you'll get something going, and then it's very difficult to maintain and fix it when it breaks and make small changes. But it really is sort of the only way to go. And my only advice is to be prepared for continual upgrades and improvements as your attention can be spared. Right, so in summary, we've covered why you might want to be a UTCK producing laboratory and the various steps to embarking on this path, some of the basic hardware and software components up to a minimum UTCK realization done only with the time interval counter and a pulse reference. A very important piece of this, the links and calibration step, will be covered in just the next talk. We covered in detail a bit about the clock data reporting and how to initialize the whole thing with the name of the second. We've talked about some ways to extend the minimum into higher resolution measurement, resiliency of hardware and software. And I won't diverge into it, but if you download the slides, there'll be three sort of examples in Python showing typical things that we do, and you could think of them as hello worlds to get started if you've never done Python at all. A final piece of advice: if you're a bear waiting to take the leap, I recommend just starting. Anything worth doing, and UTCK is worth doing, is still worth doing even poorly. Don't wait for perfect. Get started with the minimum and make continual improvements. That's my advice, and I hope there's time for questions. Thank you very much for your attention today. Cheers.
Thank you, Jeff. That was really nice talk. We do have just a few minutes for questions. If folks, so Patrizia, do you have a question or were you clapping? Okay. Are there any questions? It's very clear, Jeff.
Yeah, so if there are no questions, I have one.
Okay.
Jeff, I was always said that it is better not to touch the clock, to steer it, not to touch the internal C field or whatever can be the physical mechanism which steers the frequency of the clock. It is better to keep it quiet and use an external microstepper. It seems you are saying that conversely, two solutions are equivalent.
I think you're right. I think it is best to only affect the synthesizer. In particular, when I mention making an analog change, like to the C field of a clock or maybe a temperature, I guess I'd recommend that at most once when you first start the clock. And if it is a cesium beam clock or better, you may never have to do it at all. I certainly wouldn't recommend making an analog change for a steered clock in the UTC timescale because it's impossible to know accurately what frequency you've changed with an analog step. So I guess I would say if you're going to do that, do it just once, or in the case of a hydrogen maser, there are times every 5-10 years with some models where an analog change is necessary to the quartz oscillator inside to keep its phase lock within control bandwidth. That is an analog change that you will have to make from time to time. It turns out not to affect the atomic clock portion, but I still wanted to mention that there may come a time where you have to turn a screw in an atomic clock. But you're right, it's not an ideal method for steering frequency, especially for a reported steered clock standard. On the other hand, there are synthesizer components within a clock that bridge between the quartz crystal oscillator and the output, or the quartz crystal oscillator and the atomic standard. And at least if you touch that synthesizer, you can make the change with some amount of accuracy. The disadvantage is that most clocks as built don't allow a fine degree of precision. For example, a popular cesium beam product allows a quantized step of about 5 parts in 10 to the 15, I think. And that's a little coarse for our business. So that comes with disadvantages. I think you're right. I would recommend a synthesized offset generator, but I understand it's an extra expense, complexity, and cost, and you can accomplish it with some downsides with a direct steer of an atomic clock synthesizer, but I thank you for bringing up the issue.
Yeah, that was a great question. Thank you, Patrizia. So let's keep going. So thank you, Jeff, again. Oh, no, well, we do. I just saw one new question. Okay,
Sorry.
quick one. You're
I
good.
was just wondering, in your slides, you always measured from the falling edge of the pulses. Was this just graphics, or do you actually use the falling edge of the pulses, for example, the 1 PBS?
No, it's the rising edge. Some of my group members pointed the same thing, but I drew it in a way that's opposite to an oscilloscope. So their pulses coming down a wire and being measured at the rising edge. But you're not alone in having misunderstood the slide, which means that I'm the strange one, that's no surprise to anybody.
Good. Using the rising edge is the way to go, because most equipment also do that, right?
Yes, I agree. That was what is intended, but I'm sorry it came across as worse.
Thanks.
Okay, thank you for the question. So we'll move on. And next we'll hear a talk presented by our colleagues Calvin Lin and Giulio Tagliaferro. Calvin studied physics and astronomy, has been working at the National Time Standard and Frequency Lab, telecommunication laboratories in Taiwan since the mid-1990s. And he's in charge of the national timescale in Taiwan. He's an expert in algorithms, GNSS, two-way time and frequency transfer, and more, calibrations included. And Giulio received his PhD in environmental and infrastructure engineering from the Politecnico di Milano in 2021. And he studied topics related to GNSS measurements. He's been at the BIPM time department as a staff member there since 2022. And Calvin and Giulio will share this presentation about GNSS time transfer links with the BIPM measurements and calibration. So welcome, Calvin and Giulio.
Hello, yeah, I'm Calvin Lin. Yeah.
Hi, Calvin.
Yeah, I try to share my screen. So, is it
Looks
okay?
good. It's good.
Okay.
Thank you.
Okay. Thanks, Liz, for the introduction. In this session, Giulio from BIPN and I from TR Taiwan will discuss the GNSS time transfer link with BIPN, including the measurements and calibration. We will briefly discuss how to set up a GNSS station for the time comparison between several UTC labs. And at the first, we will mention the necessary facility used for GNSS time transfer, including the timescale system and your GNSS receiver system. And before we implement the GNSS time transfer, we also need something like we had a defined UTC K point. And we had to install the GNSS receiver and including the cable connection. And then we had to measure the reference delay and internal cable delay and calibrate the internal delay. So after that, Julio of the BIPN will take over the next topic, including the calibration service provided by CCTF BIPN Group 1, Group 2 system, and how to apply GNSS calibration, the contact information of each regional metrology organization, and what kind of things when you're doing the calibration trip you should do. And once if you have a new receiver, you can transfer internal delay from a calibrated receiver. And you can use the two kinds of software, DC Aeronex and R2 CGTTS common view. And also Julia will talk about that. And he will also talk about how to write down a calibration report to BIPN for approval. And the final, Julia will also talk about the uncertainty agent of UTC link and conclude this session. And thank you, Jeff. Just gave us a wonderful talk about the time scale. Here I just briefly talk about what kind of time scale we have. So a typical UTC time scale will including reference frequency standard like hydrogen mason or a season standard, and still by microphase data. And for multiple use, it may distribute is 1 PPS or phase by a 1 PPS distribution amplifier, and distribute their frequency using a frequency distribution amplifier. And to contribute to UTC, you have to compare your UTC point with the other UTC time scale. We can use a geosatellite for two-way satellite time frequency transfer, or you use an optical fiber to do two-way optical time transfer. But we will, in this section, we will focus on GNSS time transfer because it's most convenient and inexpensive. So before we doing GNSS time transfer, we had to have installed the GNSS receiver. For GNSS receiver used for time transfer, we hope okay, the first is internal oscillator could be locked with an external frequency reference. And its internal reference point could be locked with an external 1 PPS reference. That's a typical your UTCK point. And it should generate a right next and CGTTS file output. And okay, is better can auto upload the file of Runx file and the CGTTS file to BIPN FTP. And those are typical used receiver like GTR 55, POLARX 5, or TTS 5, you can choose. Yeah. Otherwise, of course, you can do it manually. If your receiver can generate right next, you can convert your right next into CGTTS and upload. So, and for the antenna, the most important is choose your solid antenna monument installed in an open sky, and use a choke and ring antenna to reduce the multipass if it's possible. And if it's possible, you can choose a phase center offset and phase center variation already calibrated model. You can find the model list on those two websites. Okay, for antenna cable, so consider the inclination. So it's better to use a low loss cable or a short cable. And if for consider reducing the temperature effect, you can use a phase stabilized model. And you should select a good connector. N-type or TNC are much better than BNC, and adapter. Please be careful to the impedance. The impedance mismatch may cause a signal refraction. So the typical used model type like Angel Helix or LNR 400 or LNR 300. And the RG55 is not recommended because it's not used for high frequency. Okay, so once you install your GNSS receiver, to achieve the nanosecond level GNSS time transfer, is also need to measure the delay of antenna and the reference cable. And you had to calibrate the receiver internal delay and compensate and generate the RINEX or CGTTS file used for time transfer. Okay, here we talk about the receiver instrument delay. Actually, the pseudo range, the GNSS receiver record are the distance between the center of the GNSS satellite antenna to the center of your receiver antenna. Yeah, so we need to compensate the delay from the center of the antenna to the reference point inside your receiver. And what we want to compare is your reference clock, not the reference point inside your receiver. So we had to compensate the delay from the latch point inside the receiver to your UTC-K reference point. And also the receiver need time to process the signal. So we need to compensate the signal processing delay. So a typical GNSS station delay is composites of those kind of things. The first is antenna delay. Typical we denote is XS. And antenna cable delay, we denote is XC. And the receiver hardware delay, we denote is XR. And the delay from the receiver 1 PPS in to the reference point inside your receiver, we denote is XO. And the delay from the reference point to the 1 PPS in, your reference point to 1 PPS in, we denote is XP. So the cable delay is equal to XC. And we named this internal delay to be XS plus XR, is antenna's delay and your receiver delay. And the reference delay is XO plus XP. And here we define the total delay to be the total electronic delay between the phase center of the antenna and the time reference point. So the total delay is equal to the cable delay plus internal delay minus reference delay. Okay, so for the nanosecond time transfer, we had to measure the cable delay, antenna cable delay, reference delay, and the calibrated internal delay. The first, we will talk about how to measure the cable delay. It's quite easy. The most easy way is usually time interval counter. And you can use the half lambda method or a vector and analyzer. but it's so complicated. So here we just talk about how to use a time interval counter to measure the cable delay. You can connect 1 PPS signal in the T connector on the star channel of the time interval counter, and then connect your antenna cable to the stop channel of the time interval counter. So it's a quite simple. The reading is roughly equal to your antenna cable delay. Okay, we all know the signal propagate in your antenna cable is L1 and L2, but the Daniel already published a paper. Is is roughly equal the real propagation delay. So the time interval counter method is roughly okay for the cable delay measurement. But another case is if your antenna cable cannot be tilted down, at that time you can disconnect your antenna cable at antenna end like that, and connect the other end of the antenna cable to oscilloscope by a T connector, and connect 1 PPS signal to the T connector. And the free end will reflect the 1 PPS signal back to the oscillator channel. So we can find the two rising edge. So between the two rising edge is the signal pass through your antenna cable and reflect to the oscilloscope. So the cable delay you can roughly divide by 2. So that's another tricky way if your antenna cable cannot be tilted down. So for the reference delay measurement, so for precision, we typically use aligned 1 PPS to represent your integer second. A typical definition point of a time scale can be said to be a selected 1 PPI out at a certain trigger point. So we have several choice. The first, someone will define your reference point to be your microphase step, the output of your microphase stepper. And someone defined his reference point to the 1 PPS input cable connect the 1 PPS distribution amplifier. And the third is someone will select an output channel of 1 PPS distribution amplifier, like that. And maybe I can recommend the third one because it's the most convenient. Okay, so for the reference delay measurement, so we had to measure the delay from the reference point to the receiver reference point. So the definition is equal to XP plus XO. But so the XP is the delay from the reference point to the 1 PPS in of the receiver. So it's easy to measure. Is just measure the cable 1 PPS reference cable delay if your reference point is just your 1 PPS cable connect. And so, but for XO, it's from 1 PPS in to the latch point. We have several cases. For case 1, the latch point is synced with the input 1 PPS, like the receiver or potential Pro X5 TR. If we set the auto compensation on, and the peak time TTS3 peak time TTS5 or main set GTR51, GTR55. In those kind of case, the XO equal to 0, so we know we don't need to measure the XO. And in case 2, the latch point is synced with the input frequency and 1 PPS. So like ProX 2, ProX 3, or ProX 4, or the ProX 5, if the auto compensation set to be off, or some other receiver. So it's need to measure the reference delay case by case. You can see BIP and GNS calibration annual X1 for the detail. So to measure the reference delay, we have a simple measure with pivot mask. It can eliminate as much measurement bias as possible. So you just simply connect your one cable 1 to a pivot point, and connect another cable to your UTC K reference point. And that is your receiver 1 PPS 1 reference cable. And that you have a measurement 1, and connect, and then connect your receiver 1 PPS receiver cable to your 1 PPS distribution Wi-Fi point, and use a FF connector to connect the cable 2. And you have a measurement 2, as is a simple, your reference delay will equal to the measurement 2 minus measurement 1. Also, if for the case 2, you can also use the pivot method to measure your reference delay. As a trick is if you have a very, very long 1 PPS reference cable, like your microphase stapler is low, or your reference point is located in the first floor, but your GNSS receiver is located at the 10th floor, so it's may hundreds meters away from, or your reference 1 PPS reference cable is may 100 to 200 meters long. So and that those kind of case, you can regenerate your 1 PPS using a 1 PPS generator or another microphase stapler, but there's need extra budget. Or you can define your definition point to be a certain cycle of 5 or 10 megahertz sine wave. And you can use a 1 PPS to define the cycle in a certain trigger level. Okay, but it's a complex, or you do nothing, use an unstable reference point. Okay. Once we measure the antenna cable delay and your reference delay, now we will talk about the internal delay calibration. And actually, you can calibrate your internal delay by yourself and using a GNSS signal simulator, but it's expensive and complex, and it's not traceable. So we will not talk this time. And so another way to calibrate your internal delay is so-called differential calibration with closure. So its principle is we use a reference receiver and a travel receiver to calibrate a visited receiver and use a common clock difference. And the first at the initial stage, we record the difference between the travel receiver and the reference receiver. And at the remote stage, we record the travel receiver, the difference between travel receiver and the visited receiver. And at the closure stage, we measure the travel receiver minus reference receiver again. Okay, but before we calculate or calibrate your internal delay, your internal delay, because of the reference point and the point the travel receiver connect may not be the same. So we had to measure the the delay from your reference point to your calibration point. It's also simple. You can connect cable A and cable B. So the delay from the reference point to the calibration point is the time interval counter reading compensate the delay of cable A and B. But okay, and we can also use the pivot method similar to the reference delay measurement. We can connect cable 1 and cable 2, any cable 1 and cable 2, and connect at the travel receiver reference point for measurement 2, and the reference delay, the delay from the reference point to the calibration point is simple to get is a measurement 2 minus measurement 1. Okay, once we measure the difference between the low difference between travel receiver to the reference receiver, the travel receiver to the visited receiver, and the travel receiver to the calibration point of the travel receiver to the reference point, and we can use the CCD residue to get your internal delay. So the first, we know the low difference between the two receiver is the total delay difference. So we can have the reference delay equal to the reference delay in visited side and the reference side is equal to calibration delay plus the delay from the reference point to your calibration point. And we know the total delay is the system delay minus reference delay. Okay, if in the so-called the system delay is the cable delay plus the internal delay, and we know the total delay is the system delay minus reference delay. Okay. So at the initial stage T1, we have the total delay, the equation 1, and at the remote stage time 2, we have equation 2, and for the closure stage T3, so there's equation 3. So if the total delay of the reference and traveling receiver are stationary within a limited uncertainty in from T1 to T3, so we have the total delay, the reference of the total delay at T1 equal to the total delay of the reference receiver at T3. And for traveling receiver, the T1 equal T2 equal T3. So we can combine the equation 1, equation 2, and equation 3. So the total delay of the visited receiver is quite simple. It's equal to the total delay of the receiver minus the row difference between reference receiver and travel receiver plus the row difference between the travel receiver and the visited receiver, and compensate the delay from the reference point to the calibration point at the reference site and the visited site. And once we get the total delay of the visited receiver, the internal delay of the visited receiver is equal to the total delay minus the cable delay and plus the reference delay. Okay, but for the differential calibration, we had to know all the measurement error of the reference delay and the cable delay. And the delay from a reference point to the calibration point will be induced into the internal delay calibration result. So if the calibration point is the same as the reference point, and at that time, we don't need to measure the delta reference delay, reference point, the delay from the reference point to the calibration point. This will reduce the calibration uncertainty. And in some of cases, it's not easy to measure the internal cable delay. I know at some lab, the antenna cable delay are already fixed. It's not to measured. So at that time, you can use the system delay instead. And you just need to measure the reference delay only. And if it's not easy to measure the cable delay and the reference delay, for example, it's XO is not equal to zero. And for simplify, you can use the total delay instead. And the advantage of using the total delay and the system delay is you can avoid the complex measurement and reduce the uncertainty. But for the disadvantage is you need to recalibrate again whenever you change the reference cable or antenna cable. Okay, so we finish the cable delay measurement and how to calibrate the internal delay. The next topic are about the BIPN Group 1, Group 2 calibration system, internal delay transfer, and uncertainty agent of the UTC K-link will discussed by Julio. Welcome, Julio.
Hi all, can you hear me?
Yep.
Okay, so thank you, Calvin. I will take over and discuss the most bureaucratic and operational part of the calibration for UTC. So calibration for UTC are organized in a hierarchical matter, as you can see in the schema. So the BIPM does a calibration trip to calibrate the so-called G1 labs, which are selected labs who volunteer to take this role and are selected by each regional meteorological organization. And so each 2 years, the BIPM makes a calibration trips to calibrate these labs. And then at the request of the other labs, the G1 labs makes other calibration trip to calibrate all the labs participating in UTC. For each calibration trip, a report is produced, is validated by BIPM, and all the final values are stored in the BIPM database. Also, to easy the procedure, each calibration trips has a unique calibration identifier, which is assigned also by the BIPM. And also the BIPM set the final uncertainty for the calibration. Next slide, please. So as we have seen, the G1 calibration is done by the BIPM, and the reference is one of the BIPM receiver. The reference value is based on a series of absolute calibration done in the past, and the values of this receiver are checked with all for stability with all of all the receiver in the G1 labs to check for variation, and if any variation is detected, the reference value is changed. And also, in case the BIPM reference receiver goes out of service, the values are transferred to a new receiver. In the last 2 G1 trips, we saw no variation of these values, and so the values being kept the same. And you can see for each regional meteorological organization, there are some designated G1 labs. So for instance, for Euramet, there is OP, PTB, ROA, and likely from the next G1 trip INRIM. For SIM, there are NIST and USNO. APMP has NICT, NIM, TL, and likely for from the next trip also CRIS, and COMET as SU. If you are not part, so if you are part of one of these regional meteorological organization, you should contact one of the designated lab to get the calibration. In the slide, you can find the link with all the person of contact for each lab. And if you are not part of one of these regional meteorological organization, you can contact any one of the G1 lab or the BIPM directly. Next slide, please. So each one you are visited by a traveling a trip, a calibration trip. It is very important that all their information are properly recorded, and to homogenize and harmonize this collection of information, the BIPM has provided an information sheet that you can fill. And is also present at the link in the bottom of the slides. And in the information sheet, you can see that you can record all the information about the system of the local and the traveling receiver. So the unique BIPM code, the types, the trigger level of the PPS, the types of the antenna, the types of the antenna cable. Next slide, please. And also very importantly, you should report the ref delay and the antenna delay measurement. And also quite important, if you use the CGGTS file in your calibration, you should report the delay that are inserted into the receiver at the moment of calibration. This is very important to avoid confusion afterwards when making calculation. And lastly, some general information about your lab. Next slide, please. Also, for clarity, to make sure once the calculation is done, there is no misunderstanding, it is important to report a diagram with the setup of the data collection. So reporting your local receiver and the traveling receiver and the connection to UTCK and to the GNSS antenna. For instance, here you can see an example of the last G1 2022 trip where the BIPM traveling box were connected to the TL timescale. Next slide, please. So once the data are collected and the measurement the calculation has been done, it's important to produce a calibration report that will be stored on the BIPM website, and it's important to give a small description of the process of the calculation and the timeline of the campaign. Also describe which data you use and the result, how you process the raw data. And also it is very important that you report all the middle calculations, so the calibration of the traveling system with respect to the reference system and the traveling system with respect to the visited system. This is quite important so we can reconstruct the values and checks for error that sometimes happen, so they are unavoidable. So providing intermediate result makes easy to spot any possible error. And finally, you should report the uncertainty of the estimation and the final values. In the annex, is typical to report the BIPM information sheet that we discussed before, and also a plot of the raw data and the TDEV analysis. Next slide, please. So, beside being visited or organizing a calibration trip, one other typical things you might want to do is to transfer the calibration of one of your installed receiver to a newly acquired receiver. And this is just one part of the procedure we discussed before. So you simply connect your receiver to the UTC timescale and measure the new receiver ref delay and cap delay. And you should record at least 7-10 days of data to do the calibration. Next slide, please. Then, as Calvin has discussed before, one can compute the raw diff, that is the difference of the two receiver total delay, and from there, with the equation already discussed before, one can reconstruct the int delay of the new receiver. Also, in this case, a small report should be produced and submitted to the BIPM for approval. In this case, if you do a calibration transfer, you will not be issued a calibration ID, but the calibration ID will be the same of the reference receiver from where you are transferring the calibration. Next slide, please. So to compute the so-called raw difference, there are two easy ways. One is to use the DCL Rinex software provided on the BIPM website. It simply takes the Rinex from the first receiver, the Rinex file from the second receiver. You input some broadcast ephemerid in a Rinex format, and the software directly computes the raw difference. This way, you don't have to compute the relative position of the two antennas, because they will be automatically computed by the software, and you can get directly the raw diff. Next slide, please. Another way to go is to transform the Rinex file into CGGTS format using the R2 CGGTS software from Royal Observatory of Belgium. And in this case, you will first transform the Rinex into CGGTS file and then do a simple common view analysis, just a difference. So you can use whatever tool to do this. Is not a complex calculation. All the complex calculations are done in the R2 CGTS software. But in this case, you should be sure that you input accurate coordinates for your antenna phase center. That should be at least 3 centimeters in accuracy. In the other method, you don't need to compute, so might be more convenient, but depends on your preference. Next slide, please. So once you have your system calibrated, it is very important that in the CGGTS file that you report to the BIPM, all the calibration values are present. So you can see, for instance, the header of one CGGTS file, and also very important, the calibration ID of approved by the BIPM should also be in the file. This is very important because this way, when circular T is computed, the software who is computing the circular T is able to automatically detect your calibration. So please remember to add the calibration ID in your file. Next slide, please. So it's also very important to discuss uncertainty contribution of the relative calibration measurement, and that should be reported in the calibration report. So first of all, you can check in case you are doing a calibration trip, you can check the misclosure between the calibration between the reference and the traveling receiver at the opening and the closing of the campaign. And this will quantify also any change in the hardware of the traveling receiver you had during the campaign. Then the uncertainty coming from the so-called raw diff measurement is typically estimated by using the time deviation of the raw diff time series, either at 1 day or using the floor value of the time dev. Also, the position error of the antenna, the relative position between antenna at the reference and visit site should be quantified. If you use the DCL Renex software, this is automatically computed using phase data, and so should be less than 3 centimeter. Also, you should evaluate a multipath effect. And then, of course, all the uncertainty related to the cable measurement discussed by Calvin. Next slide, please. In UTC, in circular T, there is also an aging part to your. No, sorry. To harmonize the situation, the BIPM has, with the help of the CCTF working group, has decided some standard uncertainty for the different type of calibration. So typically 1.5 nanosecond is assigned to a group 1 trip. 2.5 nanosecond of uncertainty is assigned to a group 2 trip. And if you don't, you are not visited by a calibration trip, but you send directly your receiver to another lab to be calibrated, this is called direct calibration, and is typically assigned 4 nanoseconds. And then if you are not visited by a group 2 trip, you might be calibrated by another lab or by a manufacturer. And in this case, if the calibration is authorized by the BIPN, you will likely get an uncertainty between 5 and 7 nanoseconds. It is important to remark that these are the minimum value, let's say, but if in the calibration process any big source of uncertainty is detected or is quantified, there might be a penalty value to increase the uncertainty to reflect the real value. So it could be worse in some special case. Next slide, please. And finally, the calibration uncertainty evolves with time. So there is an aging term, which is computed using the formula you see in the slide. So for the first year, no aging is applied, and then it is 0.4 nanosecond per square root of time in months minus 1 nanosecond. And after 10 years, the aging part is set to 20 nanosecond. And after that, it increased by 20 nanosecond per year. This is this last rule, which will be introduced from the next month, is to encourage UTC labs to calibrate regularly their links. And you will see these uncertainties in the section 5 of the circular and you can see an example in the slide. Next slide, please. So coming to the conclusion, we have discussed how to carefully define and maintain your time scale and select the GNSS receiver, antenna, cables, and how to install them. Also, very importantly, how to measure all the relevant delays which plays a role in GNSS time transfer, and also how to calibrate the hardware delay. Then it is important that you contact one relevant G1 labs to apply for a calibration, and you transfer your calibration value to the newly installed receiver. Also, it is recommended that your hardware are calibrated regularly, ideally each 2-3 years. And that concludes the presentation. I don't know if there is time for any question. If there is, we will be happy to answer them.
You, Julio and Calvin, we're running a little bit behind. We could take one question if someone has a urgent question. And not seeing any, but thank you very much for the very useful information that you presented. So we'll continue. And next we'll hear from Patrizia Tavella and Aurelie Harmonies. Patrizia is the director of the time department at the BIPM, and she also serves as executive secretary of the CCTF. She's a theoretical physicist with the PhD in metrology from the Politecnico di Torino. She worked at INRAM on time and frequency metrology for 30 years before going to the BIPM, so she has a lot of experience. Aurelie is a metrologist and engineer with the BIPM time department. She originally studied materials engineering at the University of Caen in Normandy. And she's been at the BIPM time department for 15 years, working on many things, including the calculation of UTC. And Patrizia and Aurelie will present the technical guidelines of the BIPM and the CCTF for the participation in UTC. So thank you.
Yeah, thank you, Liz. And I will just briefly introduce this presentation, which will be mostly given by Aurelie. I would like to focus on a few points because most of the concepts have already been explained. UTC-K is a national time scale, which is usually the basis for a legal time in each country. And only a laboratory which contributes to UTC, which belongs to the UTC community, can call its timescale a UTC-K. And also is important to say that if you have a UTC-K timescale, you are not only receiving traceability by the BIPM, but you build UTC time. So it is not only you are receiving a service, but you are part of the international time standard. In fact, what we do is put together all the free running clocks which are available in all the laboratory. Please keep in mind that UTC-K are not entered in the average. They are used as intermediate reference. And what we use are the clocks and the results. The international standard that we build together is actually in this list of difference of UTC minus UTC-K. And then we have a rapid solution, which is rapid UTC, and we also compute a posteriori the terrestrial time BIPM for other advanced use. To do that, we need the clock, we need calibrated time transfer equipment, and we have a web page that, as Jeff said, maybe you have to read and read again. And here we have in particularly the guideline for the participation to UTC and rapid UTC. If the guideline is not clear, please let us know, because we understand that sometimes the language is not always immediate. There are two topics on which I would like to draw your attention. We still use a recommendation from 1993 from the Consultative Committee for the Definition of the Second, which is the old name of the CCTF, recommending UTC-K to be within 100 nanoseconds with respect to UTC. This recommendation is now 30 years old, and at the inside CCTF, we are wondering if it is still updated, if we should change it. And so it would be important to have your feedback and to see which are the needs of your user. And another concept which is important is that once you are in circular T, you contribute to UTC and you have traceability through because you know the difference between UTC and UTCK, but still you may need an additional step, which is what is requested by the mutual recognition and arrangement if you want to sell calibration services and issue certificates. If you want to say that your certificate is equivalent to any other certificate issued in the world, and that your national standard is equivalent to any other national standard, you need to do something more. Particularly, you need to prove that your standards are equivalent to the other. You need to be part of the key comparison that in our case is called K1 UTC, and you need to demonstrate that you work in a quality system. So this may be needed only for some laboratory. So with that, I leave the floor to Aurélie.
Yes, okay. Do you hear me well?
Yes.
Okay, perfect, thank you. Okay, so I will say a few words about the technical guidelines for UTC Lab. So as Patricia said, we are providing a service, but for that we need your inputs. So I will focus on the input data you are providing to us and on the BIPM time department database and FTP server, which is the service we are providing. So the general guideline can be found here and are up to date. Okay. So I will say some words about the input data to be submitted. Jeff already talked about the FTP submission. I will say a few words, and we will see the different types of the data file that can be sent to the BIPM. And I will do that not looking at the standard format, but more on specific issues we are facing regularly when computing the circularity to spot on these aspects. Then I will speak about the output we are providing as a service. So the products that are available, the 2 APIs that are currently running, and the FTP products that are available, the data file examples and what to do with them. And I will say a few words about the consultation portal. So first of all, when you need to report the data to the BIPM, you need to do that on the FTP. So this is done through FTP or FTP secure protocol. So one point that could be useful to pay attention is that the data should be transferred in ASCII mode, except for RINEX, which are compressed and must be uploaded in binary mode. So the FTP is made so that every lab has its own folder, and there is no permission to write on other laboratories. So we secure this aspect. So there are 2 different submissions. So there is one submission for UTC and one submission for rapid UTC. So there are 2 independent submissions. As you can see, the architecture is not the same. So you need to send file in 2 different ways, and we strongly recommend that you do it on a daily and automatic way. So you can also remember that the deadline to provide the data for the circularity is the 4th day of the following month. It happens that I wrote emails a bit earlier, but this is the rule. And for rapid UTC, you have until day +2 at noon to provide the data. So here is a view of all the kind of files you are likely to provide and we have to process. So as you can see, this is a bit complex, and we strongly encourage you to do that in an automated way to avoid typos in the file names or whatever, because the file name is the basis on which our process is working. So if it is not correctly named, the data won't be processed. So regarding the file format, the data have to be provided in ASCII format. We often have an issue that is that we guess the clock files are done in a manual way. And so we have tabulation characters. So this is an issue for us for the moment. So regarding the clock files, as Jeff said, you need to provide the clock file to contribute to TAI. And so some of the participating laboratories are not providing these files. So again, we encourage you to provide these files, even with the 0 column that Jeff's have shown, because that way your clock you are running will participate really in the TAI computation and have a weight. So the clock file is the reporting of the UTC K- clock at midnight. There are two specific issues we are facing regularly, which are that clock values are growing, and at a certain point exceed the range, which is a 9-digit numeric range. So in this case, we encourage you to do a kind of resynchronization of the clock, a big step, and so to provide aside the correction that has been applied. And this way, the value UTC K- clock will come back in a normal range, and we will be able to deal with this clock. Okay, another point that maybe is not well known, the format has been defined to have maximum 5 measurements on each line. Okay, so to remember, there are 2 different clock files for UTC and rapid UTC. So for UTC, it is for each standard MJD aiding by 4 or 9. And for rapid UTC, this is the same, but these are daily clocks we provided for each MJD. So regarding the clock step correction, so any clock presenting a characteristic step has to be compensated to keep the clock being weighted. So the laboratory has to provide information about the clock step, the date, and the amount. And the amount has to be reported following this formula. And we all often have issues because the signs are reported with wrong. The steps are reported with wrong sign. And so when we process the data, it comes crazy things. So this is a point that you should pay attention mostly. So here is how the clock corrections have to be reported in the clock file. Here I will go fast because Julie already talked about that. So in the CGGTTS files, the important things are the antenna phase center coordinates. So in case you have RINEX, we can process the antenna phase center coordinates to be introduced in your CGGTTS header. So you can ask us. And the other point is the insertion of the calibration values. And it is really important for us that you pay attention to have the identifier of the corresponding trip that is well reported following this scheme in the CGGTTS. It allows us to detect automatically the incorporated calibration and to have a section 5 that is up to date. Regarding the RINEX files, so these are the most heavy files because there are many constellations and many observations. We support RINEX version 2, RINEX version 3, but they have to remain with a short file name when they are reported. We only ask daily observation data file because some laboratories are sending also navigation files or several files for a day, but it takes some volume on the server. So we would appreciate if you could limit to the essential, which is 1 file per day per receiver, to save a bit of space on the server. The RINEX has to be Unix compressed and possibly Atanaka compressed too, also to save space. There is a header file that has to be provided for the use of PPP in circularity. And another point to have the PPP in circularity is the antenna type and radom, which is in the RINEX header. You have to ensure that this antenna is well characterized and by the IGS, and that it is well referenced, so that we can process correctly the PPP. Else, we are not able to run the PPP and use it in the circularity. That's a pity. So here is an example of the header file that has to be provided beside the RINEX to apply the calibration to the RINEX. So this is just a simple copy of the CGTTS files. So if you are providing RINEX, please do not forget to upload the new file each time the parameter is modified. Regarding the two-way file, so here is the format. It has been defined in the ITU recommendation, and it does not present a regular issue from our point of view. In the case your receiver reference is not directly UTC-K, but another reference, you need to provide an additional file that is called LZ. It's a kind of link to UTC to link your reference to UTC-K. So this is just a simple file with 2 columns. Again, the documentation is available online if you need to see more on the format. Regarding the primary and secondary frequency standards, so here is how the ASCII data have to be reported. So please note that since March, first March, the PDF reports have to be uploaded directly on the FTP, no more sent by email for a practical reason. So, and now the PDF reports are considered as documentation, and they are still made available online after the circularity is published. There is one point that maybe is not obvious to you if you are providing primary and secondary frequency standards. It is that it is often required to split evaluations periods, because if there is any issue on the time link or in the reference clock, it is not possible to use a full batch, complete batch continuous over the months. So usually we detect that only near the end of the circularity computation. It requires time to write us and leave you time to do your checks, and it is quite time demanding issue that we often face, and this has to be quite a fine check to be done, because 1 nanosecond, which happen on the chain, either in the link or in the clock, in the end it gives 4 10⁻16 on the frequency of the primary frequency standard. So it is significant, and we have to be very pay special attention to the links when they are the fountain attached on the laboratory. So now we move to the output data. The BIPM is providing a machine-readable product and service to support automatized used by end user. So this is in open access. So for many years, most of the data are provided in ASCII formats. Since 2018, we added new files, column-free files and cumulative files. So this is easier for you if you want to do some treatments on this data. On February 2020, we launched the API UTC, which provides a subset of products in standard file exchange format. And last year, in June, we started the API CCTF, which provides the list of the recommended values of frequency standards and their validity. So just to say a few words, the API on UTC provide data in either text, comma, separated value, JSON formats. So these are standard exchange format. And you can access to information UTC minus UTCK, UTC rapid minus UTCK, and UTC minus GNSS times. And if the staff capacity is enough, we plan to make this evolve in the future. If you are regular user of the API, I encourage you to subscribe to the newsletter so that you will be kept informed in case there are some changes. So it's good to be informed. Here is a kind of request you can send the command line that can be sent to the API, and here comes the results. So in the various formats. So from this results, you can do your own script using existing libraries, whatever code you want, but then to plot directly the data. Please be informed that the next circularity will be modified, but there will be no impact for the API user. The changes will be made directly inside the API. For the CCTF, so the API has been developed to support automatization of digital calibration certificate. So for example, here you can request the recommended frequency value for standard frequency. I took the case of the strontium, the 88. And here is the kind of command you can run. And here is the XML file you got in output with the corresponding reference frequency. So this is in open access and you can use it for almost 1 year. Here is a full list of what is available on the FTP. So you are, I think, mostly interested in the circularity. There are also files, UTC minus UTCK, for example, which is a simpler way to read the section 1 of the circularity automatically. So it's better to go to read directly this file. There are some diagnostics statistics. So regarding the clocks, your time links, when there are several time links, comparison between them. So it's useful for you if you want to monitor how your clock behave, and also for the receivers. Okay, here is an example of ASCII files that are on the FTP. This is often in column, so quite easy to read. And also here again, you can develop your own script with the language you want, but this will be based on this online available results, so you can automatize the process. So there is also the consultation portal, so webtai.bipm.org. On it, you can find the guidelines for participation. So as for the file format I showed above, the rules for participation, the status of the participating laboratories, the equipment, calibration status, the statistics on the clocks. There are also some plots that are available. You can access to the FTP and the APIs through this portal. So this is a good way to ensure you always have the information that is up to date. So for the moment, you can find dynamic plots that they will be modified for next circularity, but at the same location. There are information about the calibration ongoing, the past calibration. All the calibration results are stored. Okay, there are also some plots about PSFS contributions, the distribution of the laboratory, and again, the equipment inventory. So for the GNSS receiver, 2-way clock in each lab. So this is quite important for us that you sometimes go and check that the information published are still okay, still valid. And one point I want to mention is that we are defining a BIPM identifier for a GNSS receiver, but in fact, this is for a system GNSS receiver plus antenna. And in the case either the receiver or the antenna is changed, we need to attribute a new identifier, and the data has to be provided with this new identifier to avoid any mixing or to ensure the things are traceable. So this is something that is probably not very known. So I wanted to point on that. There are some informations that are updated on an annual basis. Sorry. So these are tables from the previous annual reports. So the time dissemination and the time signal services, the equipment in the laboratories, which is the table 4. So I want to thank you for your inputs for 2023, which is now online. And I wanted just to mention that we have only 80% of answers. Maybe we can do better. So thank you for your attention. Remember that there is a new format for next month. And thank you for your attention.
Thank you, Aurelie and Patricia. And apologies to everyone. We're running a little behind. We still have one more talk. If there's a quick question for Aurelie, please raise your hand. And we can, okay, so Terrence Jones. Terry has a question.
Hello. Is there a penalty or is there a consequence for submitting data that has exceeded a normally acceptable uncertainty? And if there is one, does this lab get assigned a smaller weight in the calculations for UTC? And should it be explained as the reason?
The weight of the clocks is not based on the uncertainty. It's not based on the uncertainties which are in the section 1. So the weight of the clocks is not depending on the calibration status, but it can be affected if, for example, you do a calibration, then the link has a step, and then the clocks will be deweighted in this case. So there are some peculiar cases, but there is no link between the clock weight and the calibration status.
Okay, thank you. So, and we can stay on after the final talk in case there are some last questions, but let's keep going and we'll move on. So we have one final talk that will be presented by Bharath Vadakonda. And Barath is currently serving as the capacity building coordinator at the BIPM time department, and he was there for 1 year. And his position is partially supported by the IEEE UFFC Society. He got his PhD in engineering sciences from the Academy of Scientific and Innovative Research in India. And he's been working as a senior scientist in time and frequency metrology there, and in the realization of Indian Standard Time at the National Physical Laboratory in India for 11 years. And Barath's talk will cover the topic of CGG TTS data validation. So welcome, Barath.
Yeah, I think you can hear me, right?
Yes.
Yeah. Hello, everyone.
So Barath,
Yeah.
we're seeing the presenter mode, so it doesn't show your whole slide. It shows the next slide also. I wonder if you can quickly change it, or it might be hard to read.
Is it okay?
We can work like this, but it still shows the next slide, but
Okay.
maybe it's better to not use the actual presentation mode and just
Okay.
like that. Yeah.
Yeah. I'm sorry, I couldn't get this actually. Okay. So hello everyone. So since the time is actually we are behind the schedule, so let me go to the objective of my talk. So once we have the CGTS data available from the GNSS time transfer receivers, which will be shared with the BIPM for the analysis of the time transfer links. So we have developed a software which helps in validation of this CGTS data in this project, in the CBKT project. So Julio and Patricia and me contributed for this development from the last few months. So I will skip the part of the CGTTS data format description. So I want to bring to your notice that there is a course which we have developed in the BIPM e-learning platform. So for the analysis of CGTTS data. So the name of the course is as like time transfer through GNSS pseudo range measurements. So it consists of various modules, like there is a video tutorial by Dr. Pascal, chair of CCTF working group on GNSS time transfer. And there is a CGTTS interactive format description. And there is a CGTS data analyzer software, a user manual of the software, and the video demonstration of the software and the source code repository. And there is a quiz and also the references for the software. So coming to the actual demonstration of the software, so I would like to show you the actual demonstration. So can you see the slides? Can you see the web page, please?
Yes, we can see it.
Yeah, thank you. So this is the CGTTS data and format which is being made in the interactive format. So here, when you hover over the text, you can see the description of the content of the CGTTS data format, like the name of the file, the header, and the labels of the data and the data itself. So when you hover over the text, you can see the description of the text. So the most prominent one which we use is the refsys, which indicates the UTCK time difference, UTCK minus the GNSS reference, GNSS system time, and also the GNSS observation code, which indicates the frequency of the measurement and the type of the measurement and the elevation angle of the satellites, of individual satellites. So
So this is a CGTTS analyzer data software which is being developed. This is available at this URL. So that description is there in the presentation, I think. So just you can browse open this application in your internet browser. It doesn't depend on your Windows or Linux operating systems or any library packages, or the good news is it doesn't require any coding, anything. So we have an option to upload 2 receiver data files. So let me show you a sample of by uploading. I have taken 2 data sets of from 2 labs. Yeah. So here, once the data files are submitted, we can see the software automatically reads the start and end dates of the MJD. So we can select the range. Like if we want to see only from 2 days, the start date and end date, we can select accordingly as per our wish. And it automatically reads out the GNSS observation codes that are in the CGTS format. So these are the various different codes available in the particular uploaded files currently. And it reads the description from the header of the CGTTS data, like it is from the UTC PL lab of with respect to GPS. This is a GPS data at a so-and-so lab through this particular frequency. So when we select different frequencies, so we can see this plot changes, and this plot corresponds to the weighted refsys. That is the refsys values weighted as per the elevation angle of the satellite, sine square of the elevation angle of the satellite at each epoch. And this horizontal axis is the MJD, and here we can see the standard deviation, the jitter in the particular signal. And we can similarly upload the another receiver data. Here also as well, the same options are available here. So here we can see that there are different options available. So here, if you see, there is a small spike kind of observation which we can see in this L2P signals and L1P signal as well. So how, like if we are analyzing our receiver data, so we need to know, is this some disturbance in the UTC-K timescale, or it is some difference in the GNSS signals itself? So if it is in the UTC-K timescale, it should be there at the same time in all other GNSS observation codes. But here we cannot see that specific spike in the other observation codes. So moving on, so here we can zoom into the plots vertically or horizontally. So it is consistently increasing and then decreasing. So let us see how we can analyze this, what is the cause for this. So let me perform the common view. So when we click on plot common view, so just below this we will have 2 pictures. One corresponds to the individual satellites which are common at each epoch between the 2 locations, and there is another plot which is the average of average of all that satellite measurements at each epoch. So here we see that all the satellites listed are here. So we can by clicking on this, we can add or remove that particular satellites, or if we want to see only that particular satellite, double click on that. So here we have options to filter the data satellite wise or elevation mask of the satellites and the outlier. So by default, this software has a predefined limits of outlier set to be 1.5 times of the standard deviation, and the elevation mask set to be 15 degrees elevation. That means any satellite with less than 15 degrees elevation is not considered. And here it is considering all the satellites. So if we can see, like if we remove this barrier and make it allow all the outliers, if we can see what are the outliers, the data. So here one of the point is for any action on the application, the entire application reruns actually. So all the plots get refreshed, all the data get updated. So once we allow the outlier, so here we can see that there is a outlier here specifically because of the satellite number G30, right? So which is causing a 500 nanoseconds offset for some duration of time. And there is another satellite here, which is G12. So which is again causing some offset of like 250 nanoseconds for some duration of time. And there is another satellite G10. So these specific uh, satellite is having an offset during a particular period of time. Hence, there is this kind of spike we can see continuously increasing and decreasing. And because this is a weighted average, depending on the elevation of that particular satellite, it is increasing slowly and then decreasing. So the same is reflected in this common view performance finally as well. So here we can select and eliminate that particular satellite, and we can have our own we can see the performance with and without that particular satellite. So here just I have selected all the satellites. This is just taking a while to process. So this is deployed in the cloud, so anyone can access it from anywhere through internet. Yeah. So now let me remove this G30 satellite number 30. Okay. So 49.38 is the standard deviation or the jitter we can consider in the time link. So when we remove that, now it is reduced to 24.89. So that's that removal of one satellite has caused so much performance increment in the time transfer link. So again, G12, this satellite, the outlier. So now we have a better performance more. And here we have one more satellite like G10. Okay. So all the plots actually get updated during this application. So one action with one action. Yeah. So now it is 20.97 nanoseconds. So you can filter the data specifically by satellite wise or elevation wise, an outlier, or you can filter the data, perform the common view through selected date ranges and through selected frequency of time transfer between the two receivers. Right. And one more option is you can also perform the all-in view. So just below the common view, we have the all-in view. So GPS all-in view link between UTC PL and UTC Thailand and MIT with the L2P signal. So this is a description. So in the application, you can just download this picture as it is. Just click on the this option, so you can analyze, or you can download this corresponding data as a .csv file. For below every image, every picture, we have provided option to download the data of what is the current data which is processed. So what are the satellites selected? What is the start date and end date? What is the link between the two NMIs, and what is the frequency selected, and all the filtered options. So this is the application. So I hope this will be helpful for all the time and frequency community to analyze their CCTS analysis. So you can have a different set of conclusions, like just by analyzing your own CGTTS files, you can have some kind of intuitions like a linear drift, or after calibration or due to some changes in the lab, we can see a jump or some outliers, or every day there is a particular phase correction which is applied by default. So we can see that steering kind phase steering, and there is a gap in the data, and outliers. Just now the case which we have seen, common view with different frequencies like L1P and L1P, or L2P, L2P, or so here this is a L1P and this L3P ionization free combination. So we can see the pattern, ionospheric effect pattern is nullified here. And if we have only one receiver, so we perform common view. When we perform common view between the two signals, we don't have a remote station, so we upload the same files to the both receivers, and let's perform a common view. So here the effect which we can see will be the atmospheric, that combination of ionosphere and troposphere kind of effects. So we can do many such kind of observations, monitor the performance of UTC-K satellite based effect on time links. If you have only one time transfer receiver, what we can do, then effect of baseline and method of time transfer, and the effect of GNSS frequency on time transfer between two receiver stations and receiver calibration. So thank you. So you please register for the BIPM e-learning platform. So many other software applications are about to be launched in the couple of months, next months. So you can write for regarding this application for any queries to the coordinator. Right.
Thank you, Bharat. That
Yeah.
was very useful thing that
Yeah.
you've developed.
Yeah.
So,
Thank you.
are there questions for Bharat?
Yes. There is a question in the chat.
Oh, see.
Someone is asking that can we process this locally on our computer server inside? Yes, we have provided the Git source hub repository link in the BIPM learning platform, so you can use that to and process that in your local computer as well. Yeah.
Good question. Anyone else? Are there any questions for any of the speakers before we wrap up? Not seeing any. But I just want to, okay, so we have a question from Bohod John. Sorry, I'm probably not pronouncing your name very well. Go ahead.
It's okay. Good afternoon, everyone. My question is to the Aurelia. I am from Uzbekistan. We are just new in the UTC laboratories. I mentioned that not calibrated receiver will not receive information table 1 or 3 during the Aurelia presentation. Our receiver calibrated by manufacturer, it is also included in this or not?
I don't remember by heart, but you provided. I don't remember. Okay, I don't remember by heart. Did you provide the report from the ministry?
Yeah.
Okay, I am sorry. I have to check. That's a good example.
I think
Good example of use. Okay, I just went to the webtai.bipm.org site. Okay, and if I look at your laboratory, I see that there is the calibration. And if I click on the calibration, this is peak time calibration, and this just corresponds to this report, I think. This is the one you are speaking about?
Yeah.
Okay, so it's well considered, and yes, perfect. But it is easy to go and check on the website. Yes.
Karen, you have a question?
Yes, there's also the Meteo folder that hasn't been ignored in all the talks so far, and also it doesn't seem to get much love in the evaluation. I see. I tried to download some data once, and formats adherence to formats was not very strict, I have to say. Is this still used for anything, or is it mandatory to submit Meteo data?
This was decided, I think, by the CCTF so that people can share their data. So we are just the way to publish this data and make them available for anyone who is looking for. But this is just for scientific purpose, and we do not use that for the circularity, neither for rapid UTC.
Okay. Thank you.
Okay. Thank you very much to all of the speakers for the time and effort you put into preparing these talks. It was very valuable for me, and I'm sure for many or all of us here. And it's been recorded, and so it'll be even valuable down the road to people who weren't able to make it today. So thank you very much to all of the speakers. And just a reminder that there will be another technical exchange 2 weeks from today at the same time. And Patrizia put the link into the chat. It's the first comment in the chat for you to register for that as well. And we hope to see many of you there. Thank you again. And I think you can follow up with any of the speakers if you have other questions that you'd like to ask. And have a good day, evening, morning, night, everyone. Bye.
Thank you. Bye.